And we're back for another shot at estimation. Now, when we quit a few minutes ago, we had made some real progress. We had found that a statistic x bar minus mu over s, sample standard deviation, square root of n, has a t distribution. Now, we remember there are many normal distributions, and to distinguish which normal we mean, we give the mean and the standard deviation. There's only one z, but z is a normal 0, 1. There are many t distributions, and the t distribution has a parameter degrees of freedom, which I'm going to abbreviate df. Degrees of freedom tells me which t we're talking about, and that would be n minus 1. Remember, the x bar comes from a sample, so we've taken a sample of size n, and n appears down here also. Well, n also appears in this degrees of freedom parameter. So the degrees of freedom for a student's t distribution is n minus 1, where n is the sample size. Now, I think I'm going to jump right into showing you what the student's t looks like. And you see that this looks almost like a z. The difference is, instead of having the population parameter sigma, I've got an estimate of sigma that I take from the sample, and that is English letter S. So, given the similarity in the equation, it's probably not going to be a surprise to you that there's a similarity in the picture of the PDF, the probability density function for a t and a z. They look very similar. They're both bell-shaped. They're both symmetrical about a mean. For the z and for the t, both, the mean is at 0. Now, we start to get a difference, and it's a subtle difference, but out here in the tails, the t is thicker. So a z would fit underneath there. Now, if t is thicker out here, it's got to be not quite as tall in the center, because the total area under any PDF is always 1. So if I invest more of that area in the tails, then I've got less of that area to invest in the central region, since the area is always 1. So that is the look of student's t. It looks like a normal, but it's a little bit thicker out here in the tails. It's centered on 0, and it's perfectly symmetrical. Now, if I wanted to calculate something like the probability that, let's just make up something. Maybe we'll make this up. A number that I can express as x bar minus r over s over the square root of n is less than student's t is less than x bar minus l over s over the square root of n. If I wanted to calculate that probability, and you see here's my n, so I know what t I'm talking about. This t has got n minus 1 degrees of freedom. This is the n. So what we would be looking at, what this probability would be the area under this curve in this region right here. And if I wanted that to be 1 minus alpha, if that's the probability I wanted, so this is 1 minus alpha, then the area missing from this central region would be an area alpha, and if I divide it evenly between the lower tail and the upper tail, then the area in the lower tail would be alpha by 2, and the area in the upper tail would be alpha by 2. That would be the area here and here. So now we're zeroing in on how we can find this number. And you see, if I knew what this number was, I would know what L was from our original problem, because I would know X bar. I computed that from a sample. I computed S. I decided on the sample size, and if I could calculate what this number is, then I'd be able to solve for L. Well, I can do this real easy. In symbols, we would call this, where I've written this question mark, we would call that a critical value. And a better notation for it, better than just a question mark, uses the same style notation we used when we were dealing with critical values for the z distribution. I would call that point T. Now, because there are many T's, I'm going to list what degrees of freedom I have. That'll tell me which T we're talking about. And then the area to the right, that's just a notation, but the area to the right would be alpha by 2. Now, this would be a case where I know an area. I know the area to the left of this question mark, which is also this. I know the area to the left. I need to find the point on the horizontal axis. So that would be the inverse problem. Can I find that inverse T? And let's give that a whack and see what we can do here. Just suppose that we wanted to be 95% confident. So 95% would be my 1 minus alpha, or as a decimal that would be 0.95. And we saw in the previous video that that would force alpha by 2 to be 0.25. So that means that the area to the left from this boundary all the way to the left, I don't know what this boundary is yet, but I know the area all the way to the left would be 0.95. That would be the 1 minus alpha, and 0.025 would be the area in the lower tail. So we'd be looking at 975. So I would want to find a value, the value that goes right here, that would cut 975 in the lower tail. Now, I don't have Minitab up, but I've got a graphing calculator. So let's try to use the graphing calculator and see if we can figure out what the inverse T for 975 would be. Now, we looked at this calculator a few days ago. It's just a TI-84 Plus. Let's clear the screen to begin with. So we'll clear the screen, and then we want to do a probability distribution. So I'll do second distribution, and notice that 4 is the inverse T. So I'm going to select a 4, and that'll give me the inverse T. The area refers to the area to the left, 0.975. Now, unfortunately, we're making up this example, and I didn't make up a value for n, the sample size. But let's suppose we've got a sample size of, say 25. We sampled 25 men to find out what their hat size was. All right. Now let's paste that into the work area. Take a look at it before we paste. The area to the left is 975. We're under a T where the degrees of freedom, the sample size would be 26 because the degrees of freedom is 1 less than the sample size. And we're going to paste that value. And when I paste that value, that's what the command looks like. One more enter. And I see that the question mark, this value right here, did that a little bit too fast because I didn't really see what that number was, is 2.059 or 2.06 to round that off. So this value would be 2.06. That's an inverse T problem. That tells me, lets me find out what this value is right here. It's 2.06. Now, there would only be one place under this t-distribution that would cut an area of alpha by 2 in the upper tail. If I'd move this down this way, it'd be more than alpha by 2. Push it that way, it'd be less than alpha by 2. There's only one place. So x bar minus L over S over the square root of n and 2.06 have got to be exactly the same number. Where are we now? Now we can say x bar minus L over S over the square root of n is equal to 2.06, but I think I'm going to write that as t degrees of freedom alpha by 2, and then I'm going to solve for L. So we would multiply both sides by this. We would push the L over, transpose. We would push the t bar back. If I did all that, I would have L is equal to x bar minus t df alpha by 2 times s over the square root of n. Now in that original problem that we posed so long ago, we've just been able to find what that left-hand boundary would be that would give me a 1 minus alpha confidence interval. Now let me scroll up just a little bit, because using exactly the same logic, everything is parallel, we would also find that R is equal to x bar plus t alpha by 2, this time I neglected to write the degrees of freedom, times s over the square root of n. And we're clear on where all these things would come from. We found t, it's a critical value, doing the inverse lookup for the t distribution. S we calculated from our sample, it's the sample standard deviation. X bar we calculated from the sample, and n was our sample size. This much right here, it's the same as this much here, they're the very same number. This one we call E, which is the maximum error of the estimate. Sometimes called the margin of error. In polls, it's more apt to be called the margin of error. The 1 minus alpha confidence interval estimate of mu is going to be x bar plus and minus E, where E is equal to t alpha by 2, got degrees of freedom we've got to worry about, but you know what that is, s over the square root of n. So what could be easier? And in the next video we'll find some confidence intervals for you. So thank you very much for being with us again.